Without any further ado, I just want to thank I-CPIE and Atlas and NIRI for supporting this event here today and giving us the opportunity to meet with Dr. Harry today. Dr. Harry joined the faculty of Oregon State University in 2003. He is a professor of civil and construction engineering, and his expertise is in the field of hydrodynamics associated with natural hazards, especially those in a wide variety of tsunami-related problems. His extensive experience of field studies include the 1992 Nicaragua tsunami, in 1992 the Flores tsunami, 1993 Okushiri tsunami, the Great Indian Ocean tsunami in 2004, and the most recent 2011 Tohoku-oki tsunami. Before that, he also was involved in the Shikotan tsunami in 1994, the 1996 Peru tsunami, the 1998 Papua New Guinea tsunami, and his most recent contributions, or all the contributions combined actually, had numerous multidisciplinary workshops, including those in a long wave hydrodynamic and modeling tsunami measurements. So for these workshops, facilities, tsunami deposits, data repository, and tsunami scenario simulations have been enabled for our research and what we know today. The majority of these recent research activities are cooperative with applied mathematicians, numerical experts, mitigation strategists, and information technologists. He has extensive collaborative experience with Japanese scientists and engineers, for example, research program of structural control performance with Sphinx Corporation, laboratory experiments with the Public Work Research Institute and University of Tokyo, and collaborative engineering education with Tokyo University. And of course, mitigation measures with Kyoto University. So, Dr. Hale, again, thank you for accepting our invitation today, and the floor is yours.
Thank you. Thank you for coming to my talk. Really appreciate. This picture is in Fukushima, very close to the Fukushima Daiichi nuclear power plant. I was there about 1 year after. But you can take a look at this. Something going on definitely on the pavement, right? Pavement is detached, isn't it? Somehow. Or also you can see some pattern of the damage pattern on the sea walls and those kind of stuff. And as far as the pavement is concerned, I'm going to talk about that topic tomorrow. What I'm going to do today is more or less sort of the things we observe and the things we analyze. Some of those are very sort of not really special, and maybe for some people it's trivial, but see, I have a problem, right? I don't go next one. Yeah, what's going on? Let's see.
Do you want to use the arrows?
What I did something wrong.
Still see your presentation.
No, what did I do? I have to share.
I think you just switched.
How did I switch? Let's see. And then what?
Yep.
This will do it? Oh, this will do it. Just a second. I'm gonna just close this one. Here you go. So this is sort of maybe for some people it's obvious things. Tsunami is rare and high impact event. In the United States of Cascadia, return period is about 300 years, once in 300 years, right? And if you take a look at the survey results, or even the numerical results, there's a very, very strong local variability. Even like a 200-meter away, run-up height is greatly different. And also, tsunami propagates across the ocean. I think this is very important implications for this. This means if the tsunami a big earthquake happened in Japan, it's not just only for the Japan's business, but somewhere else. So it has to be, in order to work on the tsunamis, I think it has to be international. That's the way it is. And still, it's a forewarning is possible, for the earthquake. Nowadays, forewarning is possible. Few seconds, several seconds, even about 1 minute, they give you immediate forewarning and give you a signal to, at the cell phone. Tsunami case is you have a time like 20 minutes, 30 minutes. So that's the fact, right? And then it's cause devastating with human lives. So if you think about the tsunami research, you have to think about saving the human lives first. If you have a small building, you can always rebuild. If its return period is like 300 years, building is not the problem. However, the critical infrastructure is a problem. We have to keep that, right? That's the typical, okay. Clear example is 2011 Fukushima Daiichi nuclear power plant. We have to design for this, for instance, right? So those are just the things. How come I cannot do this one anymore? I don't believe this, man.
Every time that Tommy leaves the room, you have
Yeah.
this. Oh.
What did I do wrong?
Do you want to use these arrows
No.
right there?
No, I have changed the screen. I don't know.
Second.
He cannot leave from me. I don't believe this. Maybe this one? Ah, what can I do? That's not the place, right? What's going on?
I don't know. What are we having?
Oh, there you go. Can I go next one?
Yeah, that was working fine.
What did you do?
No, I just exit the screen.
No, it's not this screen, it's that
Yeah.
screen. That has something to do with the separate off from this.
I hope I'm not gonna touch anything like this. Sorry about that. Okay. So origin of the tsunami is, of course, it's a major part is the core seismic origin, right? And then landslide and the volcanic eruptions, sometimes meteorite impact. But I'm going to talk about just the core seismic origins today. Right? So something related to tsunami can happen from the earthquake, related to earthquake. So first things first, some dry fact. Let's talk about the scale for our planet. The point I wanted to make here is ocean is very, very thin compared to the horizontal scale. Depth is only 4 kilometers deep. But, you're talking about a very long horizontal scale. So that's very important things to know on this. Try to understand the tsunamis because the tsunami source is, we're talking about like 100 by 50 kilometer long. Like for instance, at the Indian Ocean tsunami, we're talking about 1,000 kilometer long and 150 kilometer wide. That means wave length is much, much longer than the depth. That's what we have to know on this to understand the tsunamis. And then, so you're gonna get the large source area. So let's just give you some example for this. This is 2004 Indian Ocean tsunamis. And the top panel, I'm just drawing the continental shelf in India on the left-hand side. And I tried to plot wave length. this wavelength was measured by the satellite. Okay. So it was 450 kilometer long for this. And this sketch is distorted. Okay, let's try to plot 101. Very flat. Very, very flat. Okay. And then here's the continental shelf. Okay. So this sketch is not representative for the tsunamis. This is not. Right? More like this. That's it. Just draw it 5 minutes ago. This is more like that. So knowing this is important to understand the tsunamis. So let's talk about the few topics. Okay, I may have too many stuff in there. My talk's going to be dictated by time, I suppose. Let's talk about the generation of the tsunami. So I said generation area is very long compared to the depth. So for that, as a precursor of the tsunami, ocean always recede first. That's what people talk about. You know, not always. I'll show you why. And then, can we predict when and where a tsunami formed the leading depression wave, like a receding wave? Maybe. Key to understand this is I'm talking about co-seismic origin of the tsunamis. I think you've seen this kind of pictures before. After 2004 Indian Ocean tsunamis, there are lots of educational videos. So they do know how tsunami is generated by the subduction zone type of the tsunamis. The important thing is the shape of the displacement created by co-seismic displacement of the bottom. Typically, you're gonna get the subsidence near the landward and upheaval for the offshore regions. That's the way it is. That's the way you're creating this lodge for the subduction zone earthquake. You know this one, right? The brick like this. So typically, for co-seismic subduction zones, earthquake creates the displacement of the bottom, subsidence near the land, and the uplift on the offshore side. That's the shape it is, right? So if that's the case, well, that's actually you can show that. For 2004 Indian Ocean tsunami is just like showing like that too. And then 2011 Japan tsunami is also shows that the uplift and subsidence. That's the sort of typical dislocation of the Earth's surface created by subduction type earthquake. So this is a sketch. If the coastline is here and the earthquake happens offshore, the shape of the displacement on the water surface is just like that. That means you have a leading depression wave, right? Let me say it again. I have a coastline here. Okay, if you have displacement, rupture zone here, displacement is like this. You do have leading depression wave in here, leading elevation wave this side. That makes sense? Okay. So that's why I just wrote it down for the leading depression wave, leading elevation wave. So that's the way it is. If you take a look at the real tsunami sign, because red part is the source of the tsunami for 2004 Indian Ocean tsunami. In the Thailand, you have a leading depression wave in the Thailand. And in this is for India, the leading elevation waves. That makes sense, right? Okay. And then if you have leading depression wave in the Thailand, the leading wave for this case is the broken waves. right? Also in Thailand, there's a very long continental shelf. In the Sri Lanka, continental shelf is narrow and the leading wave is elevation. That gives you flooding. So each location has a different kind of characteristics. This behavior can be explained by the source of the displacement, right? And but this is not always true, because ocean is flat, basically, but you have some kind of bumps, some ridges. So there's some kind of different factors involved. Ocean, you have a land mass, so that makes different. But if it's flat under ideal situations, you can predict it. Right? But if these things happen near the land, I just try to emphasize, I have a big red arrow mark. If the coastline is here, the coastline itself is going to be subsided. So that means you're going to get leading elevation waves. In other words, if the coastal line is subsided, at the same time, water displacement is also subsided, same thing. It's going to be shifted. So this red line is the one you're going to see the displacement to the water surface if you're going to observe from the shoreline. So for this, you're going to get the leading elevation waves. Right? So this is the way it is. This is 1994, I think, Shikotan tsunamis. This is the predicted displacement at the island. You're going to get top one is actual tidal gauge data. And if you're going to try to make it eliminate the large variations, you can see that it's going to be 70 centimeters subsidence, and the leading wave is elevations for these locations. I'm just going to show from the big like this. For this case, you're going to get the leading elevation wave, right? I mean, you can sort of predict such kind of stuff if you know those physics without calculating anything. And so that's sort of explained again. You're gonna get if the displacement occurs offshore, we have very likely you're leading depression wave. If these things happen right at the shoreline, then very likely you're gonna get the leading elevation wave. Incidentally, for the Chile, you're gonna get the uplift in the shorelines, and that means you're gonna get it's farther shifted to the right. So you're gonna get the leading elevation waves. So let's talk about the propagations. Okay, you can interrupt at me if you have some kind of questions. Right? So don't be shy. I'm okay. I can be beaten, no problem. Anyway, propagations. Okay. Why could 2004 Indian Ocean tsunami travel across the ocean? Without significant attenuations. And also transoceanic tsunami effect for other part too. You can actually propagate the tsunami in what? In Chile to Japan is 17,000 kilometers. Right? So key to this is source of the core seismic tsunami is elongated. There's an elongation for the source, just like this. And subduction for this directions. So source is elongated. For instance, 2004 Indian Ocean tsunami, we're talking about 1,000 kilometer long, 150 kilometer wide. And depth of the ocean is 4 kilometers. So if it's elongated, energy is sort of there has a strong directivity in the energy castings. And actually, I can show that stuff in the linear water wave theory. And you have like this. And this directivity is more pronounced if the elongation is stronger. So, simply knowing this, well, I just sort of try to demonstrate one more time. This is 1960 Syrian tsunamis. There's numerical simulations. There's a clear directivity. Here we go. And directivity, whenever we're talking about directivity, you have to think about great circle, right? We're not living on the flat land. You're circular shape. So you have to follow that great circle. That's a white arrow. So knowing this is good because we do know subduction zone. This is that the information given by USGS about 20 years ago. So you do know the shape of the location of the subduction zone. And then for that case, I wonder if you can see this red line. This red line here is very likely affected to the west coast of the United States. I can only find those two locations. So if you're talking about the long distance tsunamis, this is the place you have to worry about. Oh, I have to be very careful for this. For this theory, I'm talking about flat bottom. No, ocean is flat bottom. So of course there's some other factors, right? Bathymetry effect, maybe a Coriolis effect. Coriolis effect may be small, but so this is for the United States West Coast. Those two places are one. However, there's one more place. Those two places, Alaska. Alaska tsunami will affect west coast of the United States most likely. Again, this is the directivity for this. I can see the subduction zone direction for that. And these are numerical solutions. It does indeed shows that it casting into the west coast. So just knowing this, you can predict. As a matter of fact, year 2004, not many people about tsunamis at that time. That the night of Christmas Day, somebody called me from the Western Australia, because I'm the only few people who was working with tsunami. At that time, I used to be an expert on the tsunamis. No longer so, right? But anyway, so they called me up about 1 or 2 o'clock in the morning. They asked me if it's safe in the Western Australia. I say, I do not know, because I did not know about this. But now, if somebody's gonna call me about this, I can clearly say that effect is gonna be small. Same thing happened this year? Last year's Kamchatka tsunamis. In the Kamchatka tsunami happened last year. Japan they issued a tsunami warning, and I did know it's gonna be too much because direction is different. And I was worried about Hawaii, very much worried about Hawaii. The direction is in Hawaii. Hawaii has some kind of effect, but not too much. But you see, just knowing that let's see, just knowing the subduction zone, and if you have sources long distance, you can sort of predict where is the most important vulnerable area by distant tsunamis without calculating, without simulating anything. And another thing for that, the Alaskan tsunamis, it's affected by Crescent City and the Half Moon Bay. Just take a look at this. Isn't that interesting? Because Bay is facing south, right? The sources come from north. So that's sort of peculiar. And that's sort of, but that's the way it is. And it is sort of a very interesting topic to take a look at this. Okay, let's talk about the run-up and inundations. For this case, you have broken waves in Fukushima. And this is the same thing in Japan. This is the other side of the Japan. This is gradual flooding. So waveform is different from place to place. So if you have a long, wide continental shelf, very likely wave breaking happens. And then also, if the source is offshore, the leading wave is depression, the wave tends to break. On the other hand, if the continental shelf is very narrow, then there's no room for the long wave to break. So it's going to be gradual flooding. So you can also predict, just take a look at the bathymetry of the area. And for the summary for this, this is not my end of my talk. It's probably half away. So length scale and time scale matters. And also subduction zone and wave generation mechanism, we talk about this. We talk about directivity of the tsunamis. And we have a variety of the tsunami forms approaching the shore. Yeah. So this is just a few topics. And I'm going to give you some kind of observation from the 2011 tsunamis. Some geotechnical and structure issues. Man-type sea dikes. Okay. This is sea dikes. On the left-hand side panel, you can take a look at this. Oh, by the way, crown elevation is 8.5 meters. It's clearly overtopped. Wave height, major wave height is 11.6 meters. But anyway, in front of the dike, there's no damage. You don't see anything. In the backside is the problem. It's a huge scar hole, and the panel is gone in the backside. And so what is going on this? So for this, most of the sea dikes or sea walls are designed so that the flooding can be stopped in front of the structure. They are not fully designed for the excessive overtopping. Small overtopping is fine, like waves we're talking about. But if you have an excessive overtopping, they are not designed for that. So that's the key for this, and I work on this a little bit. So if you're gonna get excessive overtopping, you're gonna get the damage near the crown, and then also you're gonna get the severe scour behind the dike. And then, in order to explain this, this must be created by centrifugal force on the top. Centrifugal force in pulling up. And I did calculate some numbers. It did indeed, it's capable to lift those concrete panel for this. And then you're gonna get the centripetal accelerations. You're gonna get the big scar hole for this. And it's centrifugal force or centrifugal effect is, some people could not swallow it first until actually I calculated in quantitatively, and then one of my colleagues did laboratory experiments. The flow is generated from left to right, and this dashed line is for the pressure transducer measurements. And this line is at the water surface elevations. You see huge negative pressure at the crown, positive pressure at the toe. And this is indeed created by centrifugal acceleration, centrifugal force, centripetal accelerations. And so this might be a sort of a suggested, sometimes it may not be implemented, such kind of stuff. In order to reduce the centrifugal force, you only need, you should increase the you should increase the radius. You should reduce the curvature, right? So that's how you can do this. Let's see. Possible adverse effect, presence of protective structures. This is also Japan case. The arrow mark here, before and after, arrow mark is pumping house made of reinforced concrete. This is not supposed to happen. It's not supposed to happen for these reinforced concrete structures. Prior to, let's see, prior to 2011, all the reinforced concrete structure should stand with tsunami. That's what they mean in Japanese people at that time, because all the reinforced concrete structure has to be built with a code, seismic code, and they thought those are, withstand tsunamis. But that was totally wrong about 2011 tsunami case. But this is incredible. This is really incredible. What is going on? This is my conjecture. Without any seawalls, maybe it was okay. If you have a seawalls that temporarily stop the incoming energy, that energy can be accumulated in this side of the protective structure. And once it's overtopped, those energy is going to be released. And you're going to get a much, much higher flow speed. So sometimes those protection give you an adverse effect for tsunami case. Tsunami means, it's a, let's see, what they call beyond the design base event, right? So you're not going to be able to design for this kind of event, but you should at least know what's going to happen if something happens much, much more than the design base conditions. So comment, it's difficult to make accurate and quantitative predictions for the tsunamis. Protective structure may create adverse effect. I talk about this. Yeah, sometimes making it economically impractical to design the construct such kind of stuff, but still you have to know what's going to happen beyond the design-based conditions, right? And then just knowing, just thinking about that is important. If you're going to try to design some construct structure, any structure, after you make a design, you have to think, what's going to happen? Something more. And you may not be able to implement those kind of conditions for the constructions, but you might have some kind of tweak to make a little bit better chance after that. So extreme tsunami effect on buildings. That's good. I can do this. I'm glad I can do this. I'm talking about buildings. This is a little bit more computations. I'm going to talk about this. This is before and after in town of Onagawa. Just take a look at this. Okay. Distractions, wow, ooh, but just take a look at this and observe a little bit carefully. Just looking at the picture itself. Can you see this? Let me just bring back. All right, you can see that. It's like, so whenever you're going to try to think about tsunami effect, not only for tsunamis, but obviously for the tsunami effect, you're going to get the huge, huge local variabilities. Behind this large building, there's sheltered area. In here, flow must be enhanced by concentrating a flow. How are you going to predict such kind of stuff? Accurate prediction is almost impossible, isn't it? And I'm going to talk about those two buildings. This guy and this guy. Both are similar size. Right? So both are reinforced concrete. And this has a pile structures, reinforced concrete. And one of this is toppled. And this is still standing. Of course, this building has to be demolished, but still standing. This is important, right? If it's standing. So although this is too short, but if somebody's gonna evacuate on the rooftop for this, if this building is standing, they can save their lives. That's not the case for that. So that is important. Although building itself might be useless for this part, right? Useless means you have to rebuild. So I mentioned that prior 2011, all the 3-story or higher RC buildings are strong enough because of Japanese seismic code. Okay, this building is toppled and then it's dragged about 30 meters inland. So that means this is happening during the run-up, right? And this is still standing. I talk about this. So this is the location. This is the one it's toppled. This is the one it's still standing. So we're going to analyze those two buildings. One thing I'd like to talk about this is the buoyancy effect. What we want here is try to estimate the effective buoyancy force for this case. Okay? And then we also analyze this by the stabilizing body force. Oh, yeah. So body force case is first, and then we try to analyze the overturning failure. And then for simplicity, we're going to get the circular shape object. A circular shape object is equivalent to those buildings. And I think I use R equal to 5 meters, which is equivalent to the rectangular shape buildings. Oh. Yeah, okay. So what I'm going to do is the top equation is, like a horizontal force, and the second one is moment failure, right? I think this, I don't think I need to explain too much, but you're talking about that the horizontal top equation is that the net force for the horizontal direction at critical conditions. The same thing applying for the moment arm is the second equations. That's it. So we're going to calculate this. And even after calculating this, I'm going to try to make a reasonable estimate for the buoyancy force. As far as the buoyancy force is concerned, it's not like calculating like Archimedes principle, because buoyancy force on the building has to come from going steep and come underneath of the building, right? So you have to go through the soil. So pressure waves not gonna be acting on the bottom of the building instantaneously. It takes some time. So that's what I'm trying to say this. So how are you gonna estimate such kind of stuff? I use very simple model, which is diffusion by Tazagi's equations, and get some number for that consolidation coefficient. So there's going to be diffusion equation. That means some time delay. You try to find the pressure force from the bottom. You have to go through soil, so it takes some time. So that's the try to demonstrate the delay of the time. So buoyancy force, normalized buoyancy force, and normalized time for the diffusion equations. And it's a different condition. Whenever you have a deeper value for the h sub f, takes longer time to create a buoyancy force. And if it's shallow, the buoyancy force becomes much faster. The buoyancy force means you might lift the building, right? Right. So let's just calculate for those two cases. And I use okay, that's 8.9 meter, 8.9 meter. This is the way I did. And then actually I should mention just key part. In order to find flooded, if building is flooded, the water weight is gonna be in there, that's stabilizing the building, right? By the water weight, by flooding weight. So in the red one, I'm gonna assume that totally watertight, right? On the right-hand side, this one is 90% is gonna be flooded. That's the important part, which make a comparison on that. And then also drag force. Yeah, if it's totally enclosed, drag coefficient is 2. That's I use. It's a reasonable numbers. And if there's a opening, it's not so much different, but I use 1.5. Right? And then friction resistance, I use the net weight times 0.5. That's why I use this one. Still, it's reasonable numbers. So, and then you can get the condition for flooding condition from observations that Koshimura analyzed from the video images, and you got this, right? So I got velocity and the height, right? So from that, I can calculate hydrodynamic force. I can calculate moment. That's all right. And then let's think about the buoyancy force. I can calculate based upon this inundation time history. I can calculate using the diffusion equations. I can calculate the buoyancy force. Isn't that interesting? At this point, it's about 600, 700. It's somewhere around here during the run-up. If the building is watertight, it floats. Although this building has pile structures, but still it floats, right? So just the inundation itself, the concrete building simply floats. So that's probably the major reason why this one is failed. But if I compare with this hydrostatic force, if it's totally inundated inside, it's not gonna float, right? I just show you this one. I calculating this. The red one is, okay, for that horizontal force, sliding failure is happening here for the red one because net weight is so small. And on the other hand, if it's flooded, 90% path is flooded, it is okay because there is an extra weight because of flooding in the building. Okay? So that means it is important if the window is broken, if the wall is broken, if you have a breakaway wall, or breakaway windows, that save the buildings. You know what I'm talking about? You know what I'm talking about? If it's flooded, water is heavy stuff. So if it's flooded, it becomes stabilized in the buildings. If it's totally empty, it floats. Right? And I can talk about same thing for the moment failure. So this tells that the breakaway wall and the windows are not just for the reducing tsunamis horizontal force, but that gives you stabilizing the building. Okay? And then buoyancy force creates increasing pressure in the bottom. So it takes some kind of time delay. It's not instantaneous, but you have to think about that. That means you have, a deeper basement. It takes longer time to creating the buoyancy force, for it's more stabilized. So that's why I wrote it down from the bottom. Deeper the building, embedment is buried, slower the build-up process for the pore water pressure at the bottom, so it's better. And I think this is my last slide, it's showing that after the event, and this is for 2021, nobody sees that they are living here is so flat. And everybody's sort of moved to higher ground. Here's a higher ground residential houses. So artificially they elevate this ground and they're making those buildings. I saw this one in several months ago. They're making apartment building. This is in Sendai. This is good here, isn't it? It's open. So make sure this is heavy enough and putting the foundation down. And also they reduce the hydrodynamic forces. Okay. That's it. Any question or comments on argument on
I think this is for today's presentation, and okay, go ahead, ask some questions, all the questions that you may have.
yeah, that's good.
Yeah, so specifically going back to the slides where you had all the graphs shown
Graph or what?
of the ring area.
Let me just going back and see what happened. Tell me when. Keep going. Keep going. Where's the graph? Oh, very beginning. There's a graph in very beginning. Oh, there's a graph. I just don't. Huh?
This graph. So would you mind explaining or expanding on what exactly you're looking at? How do you look it up?
Okay. I'm looking at if you have earthquake happen here. Well, earthquake can be reported very quickly, within a few minutes. You can get one from the internet. If this one is happening here, then do you need to worry about in Japan? No. You do probably need to worry about going this direction. The southern tip of that Chile. Maybe Antarctic is very important for this location. And if you have, let me show you this one. If you have earthquake happen in let's see, Japan here. Yeah, that's a good one. You can see that if earthquake is happening in Japan, do you need to worry about the west coast of the US? Maybe, maybe not. As far as the directivity is concerned, if something happened here, let's see, my eyes, here you go, here. Oh, come on, man. Can you see the arrow mark? Okay, if things happen here, the place you need to watch is southern Chile. It's not the Mexico, it's not the US, but this is just based upon the directivity from the elongated source, that's it. But there are some other element, which is that the ocean bathymetry is not totally flat, but more or less it's flat. Any other questions or comments?
So I believe in like one of the images that you showed in Japan where you saw the one building toppled over and then the other one that was standing. And then you showed the apartment that was like built later on.
Yeah.
Like one thing that I noticed besides like the holes in the parking garage was that like there's also like indents on the roof. I guess it like there's like indents on the roof, so it's not like a complete square. So I think what I wanted to like follow up with was like would designing buildings to be more circular shape also like help reduce like the how much like pressure is, or how much force is being applied
Yeah.
on the building as
Yeah.
well.
Like depends on the size of the building and, yeah, I think I tried to make it, okay. Just think about the drag force. The drag coefficient for the circular one is order 1. And if you have square, it's about 2. So, of course, if you make up the, this one is a streamline. That's probably the better. So, of course, you can do such kind of stuff. But in practice, probably you're not going to do that one, right? So, if you're going to try to make a building, and building can be evacuated, so that means building cannot be toppled, then, best things you can do is probably you'd like to have, you should think about the breakaway wall or breakaway window. So that if something happens, if it's flooded, then inside is going to be also flooded. But you don't want to think about that in normal time. As I said, tsunami is very rare event and extreme event. So you just need to tweak a little bit. That's my opinion.
Thank you.
Yeah.
I see a lot of faces from my structural engineering classes, my coastal and offshore engineering classes, my finite element analysis classes. So if you look at this building and you consider that the source is close to our coastline in Japan, is there any question that you want to ask Dr. Ye today? So if we have a distant source or a near field source, would we need to take any different considerations for the design of this building?
Hmm? I have no idea. I cannot answer questions. But yeah, distant source and near
field.
local source
Yes.
has also a problem. Local source, you can feel that the ground shakings, strong ground shakings, but sometimes not, but strong ground shakings. But people think about the tsunamis. People evacuate. And for the distance tsunamis, it takes a long time to come to the shore. I forgot for the Alaskan case, 4, 5 hours, maybe 6 hours, something like this. But it takes longer time. So you might think people can evacuate in longer time, so it might be safer, right? That is not really true. If it's too long, people usually do not evacuate. So for saving people's life is not a simple business. It's a very people's behaviors. It's very difficult to predict. So this comes more than engineering. Probably it's more than psychology or anything else. It's a I can give you some interesting story about 9/11 in New York. I heard from what's his name? Some social engineering, it's not engineering, sociologist or something like this. Social scientist, I should say, in the Delaware. I think he was already gone, but he told me very interesting stories about 2011, 9/11, or 2001, 9/11. Because nobody predicted that event, right? Nobody prepared that event. I'm talking about, World Center. Right? Nobody predicts such kind of event. Nobody prepared such kind of stuff. So people usually think about it's that people get panic, totally disorder. That was not the case. That's what he told me. Next few days, they have an extremely orderly evacuation across the Hudson River. Small boat and large ferry and everything else. Okay, I'll tell you one thing. This is just my personal opinion. This is because this country. under those very strong strain conditions, people get together very quickly. You know, if you take a look at the history, you know, you have sort of a mixed society, and if you have very strained or stress conditions, people get together much easier for this country. And that's my personal opinions. All right. So how can we try to predict it from the beginning? Very difficult, right? So as an engineer, no matter what you do, you really have to think about all kinds of scenarios. Think about, you don't have to make a design or anything else, but at least you should think about it. If you think about this, you might have some kind of small additional stuff you may add it on this. And for the extreme event, that might save, a few people. And that kind of work, you're not gonna be rewarded such kind of event, right? But it's okay. Don't you think? Hey, I don't know. So our students has to give me some questions.
Yes, more questions. More questions for Dr. Yan.
Well, let's see. You see any pictures? I have another pictures for this. This is 2017 when I went there, Onagawa. All flat. So it used to be a town. It's no longer a town like this.
So we have another question.
Yep.
You remember the figure where you said a solution to it would be to increase the curvature or elongate the backspan?
Elongated source.
Further runoff.
Yes. Do you remember, or do you know like how they ended up fixing that issue, or did they fix that issue?
You're talking about that's a oh no. Is this the one you're talking about?
No.
Oh, I'm sorry.
The other one, where you showed
The runoff sketch.
Run-up sketch. Run-up sketch.
For the broken and unbroken waves, is that the one?
Broken wave, unbroken waves.
Maybe this is broken water.
It's for the breakwater?
Ah,
yeah, that one.
this one. Yeah.
Fix it. Did they?
How do I fix it? That's what I said. My suggestion, if you have enough land, if you have enough land, and of course, if you wanna, if you do this, you have a better chance. I'm not saying it fixes. You have a better chance to withstand such kind of overtopping flow because of the curvature is small. The radius of the curvature is large. Right? Yeah. So that's just the concept. But sometimes this is not going to work if you don't have a land. But you don't have to do anything of the front. Front side is fine, I'm saying. The back side and the top is the one.
Okay, and here we are looking at vertical structures. Dr. Harrier has been showing mostly vertical structures, breakwaters, buildings. What about elevated structures? Is there any other type of forces that we need to consider for our elevated structures? We briefly mentioned or have been mentioning this in our classes. So if you look at a bridge, or if you look at the pile-supported quay on a port, is there any other force component that you think we need to consider for the tsunami effects? That is a question that we need to address.
I don't know, sir.
I don't know, what is your idea? Share with us.
From previous knowledge, I would say Dr. Ware was time. It is that's the doesn't completely go through or kind of be around that construction.
What else? Yes, Chase.
Wind forces?
We can talk about wind forces, but now we are talking just about the tsunami. Dr. Ye mentioned how to calculate the overturning moment, how to determine the buoyancy and the horizontal forces. So if you think about your tsunami wave, what else should we take into consideration? Yes.
I mean, I think in the calculations, he did include like the coefficient of drag, so I guess the.
Oh, it was there. It was there.
So.
The drag was there.
Like, would another like force to consider be like inertial forces? I wasn't too sure if like that was displayed on the slides or not.
We are talking in coastal class, we are talking about the Morrison equation.
Mhm.
So Yunus is talking about
Yeah.
the inertial component and
Drag
the
force.
drag component. I am specifically mentioning the hydrodynamic component on the vertical direction. That's another one that we need to take into consideration because now the water is going under our structure and we have a big projected area on the vertical direction. So it's also something that we need to consider. More considerations that we need to take in our coastal infrastructure. What do you think it could be damaging for our structures? What else? Do you think this is an instantaneous event or a time-dependent event? Are we considering just one wave or are we considering a train of waves? Is the structure already damaged for the first impact or not? So we have been talking about this for some time now, and this is something that we also need to address. So ask questions to our extra expert, because today it's the opportunity that we have to learn more from Dr. Ya. Asala, please.
Thank you for your presentation. I have one question about combined effect
Combined effect.
of, suppose there is combined effect of current as well as plane. How do people that is structured? What kind of like, things if you are doing a kind of research on that topic, what do you think we should focus on?
You're talking about the current and the waves. That's a difficult problem here, isn't it? It also depends on that the structure, as she mentioned that bridge. If you're talking about bridge, how they usually design for bridge? They have a vertical loading for that. In my case, locomotives. That's what we learned. And they are not designed for even the lateral load, or they are not designed for the uplift. So if you have a current and wave, it's a very difficult problem too. And okay, as far as tsunami is concerned, I have to say I do not know, but most of that observation for that tsunami affected structure is not come from initial impact. They come from the subsequent flow. So that might be the clue. But also, this is also depending on the structure too, right? Some of the structure is very strong for that steady loading. Some of the structure is very strong at the short impact, short duration impact. It depends on the material of the structure too. So it's not the answer for that.
Any more questions?
You spoke a little bit about the forces when the wave hits on the shoreline with the buoyancy and scouring. Are there any additional consideration the water recedes back to the ocean?
receding back of the ocean. Receding actually gave you a very, okay. That's tomorrow, maybe, but. But if you have, okay, tsunami inundation tsunami effect takes up tens of minutes. Time scale is important. Tens of minutes, tsunami takes. And then if you have a soil, sandy soil, fine sandy soil, you're gonna get with those time scale, there might be some kind of effect. If you have heavy inundations, that creates increase in pore water pressure in the soil. If you have a rapid withdrawal, you're gonna get the pressure gradient in the pore water pressure becomes downward, meaning upward forces. Because you're gonna get the high pressure created by during the run-up, the rapid drawdown, you're gonna get normal pressure on the top, right? That gives you upper part. So that gives you a very strong instability in the soil that creates the excessive scour because the flow velocity in the drawdown is faster sometimes. So those are the important part, I guess. But as far as the withdrawal is concerned, one thing I'd like to mention is, I'd like to emphasize the time scale. Sometimes very surprising things happen for the tsunamis because we are sort of observe. Our experiences come from the wind-generated waves. If you go to the beach, you're talking about 20-second waves. So even that the long swells talking about 30 seconds. But tsunami is different. So that's why there's some kind of very surprising things could happen. So that's another interesting thing about tsunamis.
More questions?
In your opinion, what the importance do you think it's about the urbanism in the design of the for the critical events like such as tsunami? Because I noticed that the urbanism is very important to
What is more important?
Urbanism
urbanism.
for the shielding effects.
Oh, okay.
Study of the design of the city.
Yeah.
And use each structural bar construct. What is your opinion about the urbanism in the
As a mitigation
designs,
measure.
Sorry.
Urbanism as a
Oh,
mitigation measure
urbanism.
Yeah.
Yeah.
for the shielding and channeling effects.
Yeah. Those. What can we do?
What can we do?
What can we do is my answer actually, because you don't. This is my own opinion. You don't design for that, I guess, for the normal society. But we do need to consider very carefully for the critical structure, critical infrastructures. Maybe bridge is important. Yeah, bridge is also important, isn't it? I mean, very strong steel bridge versus very wimpy wooden bridge. Both are important, right? Critical structures. Because once the wimpy structure is gone, there'll be a problem for the rescue missions. So maybe bridge is also important, but you have to think about all kind of factors.
Okay, any last questions? So thank you all for being here
Yeah,
today.
thank you for
I
coming.
will see you tomorrow, and thank you to our Atlas director and co-director. Thank you to Neri. Thank you to I-CPIE. And again, help me thank Dr. Rie for today's presentation.
Thank you.
And I'll see you all tomorrow.
Let's see.